Hi everyone, I hope you are doing well. Welcome to Coding Museum. Today, we'll be designing a unique ID generator in a distributed system. Without any further ado, let's get started. For any system design interview, it's essential to follow a structured framework. The first step is to thoroughly analyze the problem and anticipate potential challenges. Make sure to think out loud. Next, discuss these features with the interviewer. Seek their input and clarify any questions you have. By the end of the requirement gathering phase, you should be able to outline both functional and non functional requirements. Identify key features you intend to address during the interviews, along with the additional features you can explore if the time permits. Once you have requirements, perform back of envelope calculations. These estimations help you gauge the system capacity and provide insights into its scalability. In the fourth step, you begin crafting the high level design, which includes defining APIs, database, and server interactions that will form the system's architecture. Then, in the fifth step, deep dive, where you focus on the scalability of each component you introduced, ensuring the design can handle growth effectively. Additionally, ensure that the system includes the feature identified during the requirement gathering phase and that it supports the back of envelope calculations. At last, you need to wrap up by summarizing your design, addressing any unresolved challenges, and discuss the potential improvements for future scalability. Let's start designing the distributed unique ID generator. When designing this, the most intuitive approach is to use auto increment feature in a database like MySQL. While this works well in single node setup, we need to consider whether it scales efficiently in distributed system. One major challenge is the risk of ID conflicts when multiple systems generate IDs independently. If we rely on a single database, it can become a bottleneck, limiting scalability. On the other hand, using multiple databases raises the risk of generating duplicate IDs unless we implement strict coordination. While database coordination techniques like global counters or distributed locks can help prevent conflict, they come up with trade offs in terms of latency and performance. So, the key question is the approach truly efficient for a large scale system? Understanding these challenges is crucial before choosing the right ID generation strategy. Now, in the requirement gathering phase, the goal is to clarify the system constraints and expectations by discussing key questions with the interviewer. For example, should the ID be unique? And the interviewer might respond, yes, every ID must be globally unique. Can the IDs be traceable or should it be completely random? Is what you can ask. As second question, then the interviewer might respond it should be random, ensuring no predictable pattern. The third question that you can ask is are there any specific restrictions on the characters used in the ID? And the interviewer might respond with yes, the ID should consist of only numeric characters from 0 to 9. What should be the maximum length of the ID? The ID should be at most 64 bits to maintain efficiency in storage and processing. And by the end of this discussion, we have a clear understanding of the key requirements which will guide you uh, and our design decisions moving forward. Now that we have gathered the key requirements, let's break them down into functional and non functional aspects. Functional requirements define what the system must do. The ID should have maximum length of 64 bits. It must be random number with no predictable pattern. Only numeric characters between 0 to 9 are allowed. Most importantly, each ID must be unique across the system. Whereas when it comes to non functional requirements, this focus on the performance and reliability of the system. Generally, we talk about CAP theorem in this case when talking about non functional requirements. So, here first we want to tackle availability. So, if one server goes down, another should still be able to generate unique IDs without disruption. And second non-functional requirement that we should handle over here is interoperability. Each server should be able to generate IDs independently without relying on coordination with the others. These requirements will shape our design choices, ensuring the system is scalable, reliable, and efficient. Now, coming towards the third stage, as we have our requirements, let's let's estimate the scale of our system using back of envelope calculations. We expect to generate 1 million IDs per minute, which translates to around 16,500 IDs per second. Each ID is 64-bit long, so the total data generated per second is 64 bits into 16,500, which is approximately equal to 1 million bits per second. While storage is always consideration, in this case, the performance of the system is far more important because we won't be actually storing the IDs, rather generating them. The ID generation process must be fast, efficient, and highly available to keep up the demand. And in most systems, we need to balance both storage and performance, but here performance takes the priority. Now let's start by examining the multi-master database approach, which is the first approach for designing a distributed unique ID generator. In this method, when a client requests a new ID, the request is sent to a server which then connects to database randomly, or other techniques like consistent hashing or round robin can be used. Each database generates ID at specific intervals, where the interval is determined by total number of database. For example, the first database would generate IDs like 1 plus n, 1 plus 2n, and so on, where n is the total number of databases. And so on, the other databases should also generate IDs. For example, the second can generate from 2, 2 plus n, 2 plus 2n, and so on. However, the main issue with this approach is that it doesn't scale well when servers are added or removed. For instance, if one server goes down, all the IDs that it was supposed to generate are no longer being created. This introduces a significant reliability concern. Now, let's go towards our second approach, which is called as ticketing server approach. In this, the system there is a single database which we refer to as a ticketing server. When a user requests an ID, it connects to client, which then fetches the ID from the table. The table is set up with a single auto increment logic, where the ID is the primary key. When a new ID is added, a replace command is executed, automatically incrementing the ID, and the update ID is then sent to the client. This approach is used by Flickr to generate unique IDs for photos, comments, and other resources. The SQL command from their article, which shows how to create the table and use the replace command, are displayed on the slide. However, one side downside of this approach is the single point of failure. If the ticketing server goes down, the entire system will be affected. To mitigate this, Flickr uses two ticketing servers for redundancy, ensuring availability even if one server fails. Now, coming towards the third and the most efficient approach, Twitter Snowflake approach, which is highly efficient for generating unique IDs. In this method, the 64-bit is broken down into several components. 1 bit for single sign bit, 41 bits for timestamp, 5 bits for data center ID, 5 bits for machine generating the ID, and 12 bits for the sequence number. This structures allows the system to generate unique IDs efficiently while ensuring scalability across multiple machines and data centers. Even this supports generating multiple IDs within the same millisecond. So talking about sign beat, we it will always be set to zero at as it is reserved for future use. In this future, in the future, it could be potentially utilized to differentiate between signed and unsigned number. And if you observe, we are towards the deep design dive phase where we discuss the Twitter Snowflake approach in detail because it's most efficient approach. Now, let's dive deep into the timestamp section, which occupies the most significant 41 bits in the ID. The timestamp is critical because as the time progresses, the IDs become naturally be sortable by time. This means that the IDs are not only unique but also provide a chronological order. The maximum timestamp that can be represented with 41 bits is 2 raised to 41 minus 1, which is approximately equal to 69 years. This gives us a timestamp within range of 69 years. After that, we would face an overflow. However, by choosing a custom epoch time close to today's date, we can delay the overflow significantly. So, for the next 69 years, the system can generate unique IDs without any issue. The epoch is the starting point from which all the unique IDs are generated. The timestamp in UTC is simply the epoch time plus the decimal representation of the 41-bit timestamp. This method ensures that IDs are tied to a precise moment in time while maintaining scalability for nearly 7 decades. Next, we have the data center ID and machine ID, both of which are allocated 5 bits each. With 5 bits, we can represent 32 possible combinations for data center and machine. This means we have up to 32 data centers and 32 machines within each data center generating unique IDs. This allows the system to scale across multiple locations and machines without the risk of ID collision, ensuring uniqueness across a large distributed system. Lastly, we have the sequence number, which is allocated 12 bits, allowing for 4096 possible values. This means that up to 4096 IDs can be generated per milliseconds. When you scale this up, it gives us a total of 4 million IDs per second, which is much greater than our requirement of 16,500 IDs that we discussed in back of envelope calculations. This gives a system a lot of headroom, ensuring it can handle even higher ID generation rate if needed without running into performance issues. In conclusion, the Twitter Snowflake design is both scalable and efficient for generating unique IDs, with UUIDs in Python offering a straightforward implementation method that could be explored in the future. But the UUID method in Python allows us to create fixed 128-bit unique IDs. So this can be changed or scaled as per the bit requirement specified by the interviewer. Additionally, clock synchronization is critical in the Twitter Snowflake approach to ensure accurate timestamps across distributed systems. Moving forward, we need to evaluate the impact of changing the 64 bits and assess whether 32 machine IDs and 32 data center IDs are sufficient or if future scaling is required to address these limitations. At last, enhancing observability and analytics is crucial for ensuring the reliability and performance of the distributed unique ID generator. Future work could focus on integrating structured logging, distributed test tracing, and real time monitoring to detect bottleneck and anomalies. Additionally, leveraging analytics on ID generation patterns can help optimize system efficiency and detect potential misuse. Thank you. That's it for the unique distributed ID generator.